Okay, so welcome back to the class, everyone. And welcome to the Zoom meeting for Zoom people. So today we're going to continue to talk about software security, and we're going to touch the 101 for reverse engineering, okay? So before I talk about anything, let's start with announcements. We have 3 announcements today. The first announcement is about extra credit. So we have been asked by students regarding whether or not there's a chance for you to win more credits. And here is the chance. So we have a cybersecurity symposium held this Friday from 10 a.m. to 3 p.m. It's going to be online. And we welcome everyone to join this symposium, participate, and you will be able to win extra credit if you participate. So there is a registration link. You can just register whenever you want. I don't think there's really a deadline for that, but just please double check, click this link and see if there is any deadline shown over there. So you need to register first in order to get the extra credit. More information has been released through Piazza, and you can also just check those information. Actually, right now, let me just click. Let's go through this information. All right, Zoom people, I suppose you can also see the link, see the Piazza page. Let me know if you can't. So again, this symposium will be held on Friday from 10 a.m. to 3 p.m. And if you need, if you like to attend and if you like to obtain the extra credit, you first need to register. And then you need to participate. And after that, you need to write a report, a brief report with a minimum of like 3 paragraphs talking about this symposium. You need to talk about, some of those talks. You need to summarize those talks and also provide your thoughts and opinion on the talk. So I want to make sure that you did listen to the talk and also do have some, opinions or some, feelings after you learn from those talks. We will have a link available from Gradescope. So once you are ready, you can just submit your report to Gradescope, and the talk will not be recorded. So you will be just like, participant or miss it. You don't really have to spend there for the entire 10 a.m. to 3 p.m., although we highly encourage you to do so. But anyways, you need to generate the report and talk about those talks. We have a bunch of talks over there. We will have a multiple keynote speakers as well as, lightning talks that talk about those cool research that has been ongoing in our lab, Adam and my lab, SEPCOM lab. And also, if you're interested in, having an intern in the future at SEPCOM lab, I highly encourage you to participate in this symposium because that will give you more ideas about what we're doing for research. And some of those may interest you, and that can be, your start point. If you're interested in doing research, or if you're interested in doing more, cool stuff regarding cybersecurity, collaborating with us as SEPCOM lab. Okay, so this is announcement number 1. Any question? Okay, question here. Do we need to attend all the talks or just one? You don't need to attend all talks, but you should not also just only attend one, like just hop there for 5 minutes and leave. That's not the point of attending a symposium, because you need to generate, again, you need to talk about those talks later on. So you need to make sure that you participated so that you can know what are those talks talking about. All right. Okay. No more questions? Good. All right. Announcement number 2. Wait a second. Let me get it back. All right. Here we go. So announcement number 2, extra dollars. So we will have a fuzzing hackathon on Saturday of April 23rd from 11:30 a.m. to 6 p.m. So it is a hackathon that your job is going to first learn what fuzzing is. And second, you're going to learn how to use a fuzzing tool, which is called Mayhem. I don't know, maybe some of you have heard about it if you have used, like do some binary analysis before or learn, existing like binary analysis tools before. So your job will be, learn how to use those tools, learn the technique, the fuzzing technique, and that's all free. And actually even better, you will get $100 credit if you learn it. And after that, you will be tasked to write fuzzing harnessing for open source projects. And it's okay that you don't know what it means by fuzzing harnessing at this point, because you will understand what fuzzing harnessing is once you participate in those like training sessions. And once you'll be able to successfully integrate Mayhem to one of those open source projects from GitHub, you will be awarded by $1,000 more. So this is like a great chance for you to learn a technique and also get some extra dollars if you'd like to have it. Also, as I said, you will be entered a raffle for an Xbox Series X. So just, even cooler award, a lottery for that. If you're interested in, you can register from this link. Again, it's gonna be on Saturday for April 23rd. So it will start from 11:30. You will be offered pizza, lunch. And after that, you will learn fuzzing probably for 2 or 3 hours. And after that, it will be just your own time that you can work on fuzzing harnessing during that time. Okay, so this is how the hackathon works. All right. Any questions regarding this hackathon? No? Good. Nice. All right. And the third announcement, you have actual assignment. I'm sorry about that, but extra assignment always need extra credit as well. So that's a good thing. We have network assignment released today. You should be able to check the assignment now. So you're following this link. It's fourth assignment and the deadline is April 15th. Yeah, so you will have about 50 challenges. That's quite a lot, but each of those challenges are relatively simple. So it's not like as hard as those AES challenges that you have to program a lot, but you still need to program probably a little bit, and that's mostly for network. So I would also again suggest you guys to start early, since although it's easy, you're gonna have 50 challenges. So make sure that you start easy so that you can get your point in time. All right. Okay, so I saw some of you guys are saying that there is a link that's broken from the Pwn Devil challenges. I will take a look, but so far I haven't observed that, but I will try to reproduce and let you guys know. But in any case, I think the assignment, the course website assignment should already be available, and you can check the info from there. And continue to let me know if you come across any like things like broken link or etc. Okay, question, yes. Yes, it's supposed to be on Plum College. It's the same like CTF, the same Plum College link that we have before. All right. Okay, so today let's continue. If you remember, last time we talked about binary, right? We talked about hexadecimal, we talked about endiness. And today we're gonna start with binary again, but look at binary from another angle, which is programs angle. So today we're gonna learn, you know, how, when we say binary, or when we say like executable program, how that looks like. So we're also gonna talk about the reverse of reverse engineering, meaning that we wanna understand the compilation process, which is turning from source code to the binary, right? And that will help us to understand, you know, we need to understand this forward order so that we can understand the reverse order clearly. So let's start with this forward order compilation first. All right, so again, you know, we know that our programs are all composed of binaries. And how do we generate those binaries, right? Because when we write a program, we usually just write it as a source code. But then something or some tool that help us to convert those programs from source code to the so-called executable file, but it's like in binary, right? Zeros and ones. And later on, we execute it and we can get the output, which is something that we have programmed in our source code languages. So ultimately, we need to, you know, or we will talk about reverse engineering, which is coming, like take an executable file and execute the result and try to understand the intention of the code or somehow like having source code in our mind. But today we're gonna do this first from this forward side, which we call compilation, which turns from, you know, turns a source code to executable file. Okay, so again, you know, from source code to something maybe .out file, if we're using like ELF format, if you just compile it on Linux. So usually in Linux, what you could do is to use a compiler called GCC. I suppose that many of you should already heard about GCC or used it intensively, right? So when you compile the code, you're actually just call GCC, the compiler, you know, feed GCC with the path of your source code, and then specify to GCC the name of the output. So here, example.c is the path of the source code, and -o is the option that you can specify the name of your output, and example.out is the output that you specify. Okay. So if you use GCC, you only need to type this one command to compile something, to compile from source code to binary file. However, if you look at how it works for GCC, it's actually composed of multiple steps. So we can divide that into 3 steps. CC1 is a compiler, and then there is AS, S as assembler. And then finally, there is a so-called LD, which is a linker that can, you know, link those like library calls like printf into the binary itself. So GCC is short for the GNU compiler collection. And that's why it's called collection, because it's not just one tool. It's actually a collection of tools that doing those processing as a pipeline. And in fact, you can, you know, get those intermediate results if you just, you know, specify these 2 more options from GCC, which is save temps. You can get those temporary files while doing this entire compilation process, and also -v. Yes.
It's also called collection because of the fact that it also is a collection of multiple languages as well.
That's true. Yes, it's also. Yes, it's also a collective of languages as well. Can I have your name? Ted. Sorry, Ted. Ted. Sorry, I'm very bad at people's names. Can you say it again? Tim. Okay, gotcha. Yes, as Tim said, the collection also means that a sort of, a bunch of languages, even including like Java. I mean, C++, of course, also like Java languages. All right. So let's continue. Okay, so now let's start to talk about this entire process. The first, as I said, is the CSE1 compiler, right? So what it's trying to do is that it converts from the source code to assembly code. And I suppose that you guys already know assembly code, right? We talk about x86, 64 assembly, so we know that those are the assembly code. And this is the job of CSE1. So it converts from source code to assembly code. And you can just only use CSE1 instead of GCC, just the CSE1 there, and then specify the output of it. It's very similar to the command that you have for GCC, so that you can, output a .s file, which is assembly code. And in this process, it also contains multiple small steps. So the first step is pre-processing. Basically, it just removes those comments, because for compiler, those comments are not useful. For us, it's useful because we programmed. But then for compiler, when it converts the source code to assembly code, comments are not necessary, are redundant. So it first remove it, and then it substitute those macros. If you define some macro, now during preprocessing, it will substitute that with the according strings. And then the third is, resolve like condition compilation, such as, if that, if you use that, and then combine source code, all source codes together into one file. So even though that you write C files into separate files, in this pre-processing procedure, it will combine all those together as one big file. Okay, and then after that, it will start to compile. So it will do, if you have had a compilation class, those steps should be you should be pretty familiar with those steps. You start with the lexical analysis, syntax analysis, semantics analysis. You will start to have those ASC trees, and then you're going to have the intermediate code generator. And after the code generator, you will then do like code optimizations. You try to improve the code, maybe by improving the performance, or condense it by the size of it. But the size of the the code, depending on what kind of optimizations that you're trying to do, or maybe like things like constant numbers, propagation, etc. And finally, we generate the code. And here the code is assembly. So this is the way that you can generate, the assembly code. And usually this is, if you are taking a compiler class, or if you will take a compiler class, this 6 steps are majorly the things that you will learn from compilation class. All right, so, the first step, as I said, is the compilation step. So you use CC1, which is part of GCC, that you will be able to convert from source code to assembly code. But then again, as a machine cannot read assembly code either, right? Machine doesn't understand what it means by MOV, move. Machine can only understand instructions, or say like binaries, like 0, 0, 1, something like that, right? And then here comes assembler. Assembler comes into play, and assembler converts assembly code to, very important, incomplete machine code. And then later I will talk about this. I will explain to you why we call it incomplete machine code. All right. So far, let's just consider this, when we say machine code, it means binaries, 0, 1, 0, 1. So assembler does this conversion, but the library functions are missing, and this is why I said this is incomplete. For example, if you call, printf, which comes from a libc, then it will be incomplete because it is not the function that you implement by yourself, but instead you call those functions from library. But then at this point, by the time that you compile and assemble, you don't really touch that library. You don't really find where the libraries are, or copy paste those library functions into your own compiled code, but instead you just put it aside. And those library functions will be resolved later on, right? So now when we do assembly, it's gonna only assemble those code that you write by yourself instead of those codes like library functions that someone has implemented for you. Okay, so after that, you will generate a so-called .o file, and that is called relocatable. So it means that it is in the so-called ELF format, but it is a relocatable, meaning that it can be relocated later on. And when we say relocate, it means that you just put library functions over there. All right. So after this, that's why if you have, sometimes if you just do GCC, or if you just write a make file and then compile a big project, you will see there are multiple .o files over there. But then that is not something that is really executable. If you just run something .o, you will not be able to run it usually in most of the cases. And what you really want, if you want to execute, is the so-called .out file, which is the actual ELF executable file. And the difference between .o and .out is library functions. So, and that is the job of linker, such as the tool called LD. So what linker does is to turn from incomplete machine code to complete machine code by incorporating those libraries, by telling this example.out file, by adding those information into example.out file, specifying, okay, where are those functions? Okay, which kind of libraries that they need to look at, and where are those functions in this particular libraries. So if you already have a .o file, then you could run this very long LD command that will link those existing libraries that has been installed in your operating system. And here specifically is Linux operating system. And then you will be able to generate an actually runnable code, which is the .out file. All right. Okay. So again, for linkers, it will make sure that the environment is ready before function main, and then it will resolve those library functions. And also it will make sure that the program will finish properly. Okay, and then combine the three steps together. We'll have the actual example.out file. And if you just use file command to take a look at the type of the file, you will see that it will say, okay, this is ELF 64-bit LSB executable. And the architecture of it is x86 64. And LSB means least significant byte. And this is what we have mentioned last time, right? So that is least ended, basically. And once we have this example.out, we can then run it. We can get the output that we are supposed to have, such as, the Harry Potter example that we had from last time. All right, so this is the entire compilation process that will also give you the, executed result. And later on, when we start to talk about reverse engineering, it mostly just giving the executable file, or maybe the executed result as well. If you run it by yourself, you want to reverse it, you want to infer the intent of the executable file. You want to understand those semantics coming from source code by looking at like those a bunch of 0, 1s, 0, 1s. And that sounds overwhelming, right? I mean, it's a bunch of 0, 1s. How can you really read zeros and ones and some combination of them and then understand, oh, this is maybe an add instruction, or maybe this is a add statement or a printf, right? The nice thing is that, you know, first we have nice tools, and also Linux ELF format, it has a very nice fixed format that can instruct you so that you can abstract those 0, 1s into higher structure and understand those layout of this entire binary. And today we're going to talk about the layout of ELF format, which is, you know, the Linux executables. Okay, so ELF. ELF is short for executable and linkable format. So remember that when we look at .o file, it said it is ELF relocatable. So it is, you know, in this format and it is linkable. And then when we have this .out file, it says it is ELF executable. So it is in this ELF format and also executable, basically. So usually for ELF format, it contains 4 different parts. Well, actually, I should, yeah, okay, I can call it 4 parts. So the first part is the program header. It's called ELF header. It's like, you know, the first thing that you want to read for an ELF binary. It specifies, it gives you the index. It tells you what the rest of the program looks like. And also it gives you the high level information. For example, you know, usually the ELF header will start with ELF, telling you that this file, when you look at it, even though that you don't know this is in ELF format, you can read the first couple bytes to know that, okay, this file itself is an ELF file. By the way, ELF is the Linux executable, and this is different from those Windows executables. So Windows executables, it's called PE executable, and it has a different format. But in our class, we're only gonna teach you about Linux executables. So that's why we're talking about ELF, and later on in those assignments, you will mostly, you know, handle, or you're gonna be mostly deal with Linux binaries. All right, and then the second part is program header table. You can find where the program header tables with the help of ELF header. That's why I have an error here. Basically, ELF header will point you to program header table. And then the program header table is a larger index. It's a table, contains, you know, small items, and each item is the smaller part later on that in this ELF program. It contains like each so-called segment. And we will talk about those segments later on as well. And then the third part is sections, or say segments. Basically, segments, a group of sections. So for example, we have compiled code, you know, where those functions that we write and assembled, and also, you know, converted to the machine code, 0, 1s. They're gonna be one section in our program, this entire program, like the actual instructions, the function that will be executed. And besides that, things such as like global variables, okay, or some like raw strings, they're all gonna be stored into the program, but they're gonna be in different sections. Like the .text section, although it's called the .text, is actually the codes, like those, you know, converted machine code for the functions that you write. And then for .data section or .ro data sections, they are like data, global data, or read-only data that you will need to use while you execute the code. All right. And then finally, there's section header tables. It is usually in the end of the program. So if you look at this entire program, this is the higher address and this is the lower address. Or think about this as you open the program, although it's binary, you just like open it using your text editor. You will see those like bytes, bytes, right? And then following those bytes, you will have this entire structure. It will start with the so-called elf header, and then followed by that will be program header tables, and those different sections, including the data that you put in your program, such as the string of like Harry Potter, those kind of string, or the the function that you write. And then followed by that is another header table that points back to those sections. And you may wonder that why we have a program header table and we also have a so-called section header table. What do they mean and how they work? Why do you need two? And we will talk about that later. And now I'll just give you a high level overview for what is this format look like. All right. Okay, so again, now let's start to talk about those details. We have this, the layout, and let's first start with elf header. Okay, so elf header is the general information, contains the general information about the binary file. Basically, it tells you about this file that is in ELF format. It tells you something like, okay, the architecture of this format, this file, like whether or not it is 32-bit or it is 64-bit. And also, where is the entry point of the code? Like when we say entry point is like the main function, those entry point of the code. And what is the endianness of the code? We mentioned about endianness last time, little endian or a big endian. So some of those binaries, they're actually in big endianness, and some of them they're in little endianness. So you need to specify that in your header file so that when your operating system executes the file, you need to read this header so that it will know which endianness does this file go for. Okay, and then instruction set, architecture, and also the position. Again, that's why we call it the header, elf header, as the start of the file. It's like without reading this header, you have no idea about this entire file. And then this gives you a nice index. It will tell us that, okay, starting from there, you can then read the rest of the content of the binary. All right? Okay, so this is a header example. And give me one more second. Let me just pull out a ELF binary, and then we can read this together. Actually, let me just make this window smaller. All right. Okay. I suppose Erin can see the both the slides and my terminal, right? And let me know if this is too small. So let's take a look at a binary. Let's take a look at this example, okay? So it's called elf header example. And this is .out file. And if you use file, you'll be able to see the file script. And now let's use a tool. Well, actually, let's start with take a look at it. Just open it. I'm gonna use Vim. You can use whatever text editor you like. So I'm gonna just use my favorite, which is Vim. Okay. This is how it looks like when you open it. It looks something that is not parsable. But you see that there is a very interesting ELF over there, right? And that is the start. That comes from the ELF header. It is part of the ELF header. In fact, if you look at here, I believe this, well, I think this three character is ELF, okay? And let me convert this because when we displayed it, those bytes are not really like, readable if it converts from the bytes to ASCII. But now let me just tell the command. Oh, okay. I know the reason, because I don't have access the, hold on. I should have access being installed already. Here we go. All right. So what yes, hackathon, exactly. So what I'm doing here is to kind of convert the the representation to show the hacks of to represent each of those bytes into hacks. That's what we talked about last time when we have those representation for each of the byte. If you remember, we talked about a byte is composed of 8 bits, and when we represent it, we usually use 2 numbers or digits that represent 1 byte, right? So here, the first byte of this program is 7F. The second is for 5, and then followed by that is for C, for 6, etc. And you see that this is same as what we see here, right? And this is the ELF header, okay? Now let's convert this, from some bytes that, okay, now we can read it, we know those bytes, but we still don't know the semantics. We don't know what it means. We only can see, okay, this is ELF 3 letters that we can understand, but what are the ELFs talking about? Let's use a tool called reelf, okay? And then let's do a -H, I suppose. That means that you read the ELF header of this particular binary. There we go. All right, so this is how it looks like. It helps you. That's why we need nice tools. It helps to abstract those information, put it into the format. And in fact, if you look at this ELF header, it's already have a fixed format. And that's why all this tool, or all you need to do is just put those values into each field, which has been defined as part of the format. And then you will be able to understand the meaning of this header. Okay, so let me make this slightly larger, since we don't need the comment line anymore. All right. Okay, so this is how it looks like. Left-hand side is the bytes of the header, and the right-hand side is the interpretation of the header. So the first couple bytes is the magic. It's a string. Basically, if you have the string, it tells you that, okay, this is the ELF format, things that you're reading. And then in this magic here, you see there's a 0, 2, right? Which is 1, 2, 3, 4, the 5th bytes. And it tells you the class of this ELF header. Like this is 64. So this is like 64 bit binary. And then followed by that is telling you the type of this ELF, which is like whether or not this little endian or like big endian. So 0, 1 specifies that it is little endian. All right. And then let's just move on. Let's ignore those bytes for now. Continue. Here, in this particular field, this 2 bytes represent the size of this header. It's always like looking at this particular 2 bytes, this position, and you will be able to know the size of this header, which in this case is 64 bytes. And pay attention. I really want you to pay attention here. Like why little endian is so important. It's so, it's in such an early position. It's because once you know that this program is in little endian, you will need this information when you start to parse the following, like those bytes information. Because this is little endian, now you read these 2 bytes, you know that this is in lower level, right? And because of like a little endianness. So least significant bytes comes to lower address. So that's why for 0, it starts, this is the lower bytes, and this is the higher bytes. So that's why when you read this 2 bytes, when you read this 2 bytes, you should read it in opposite order. So it should be hex 0040. And that's why it's equal to 64 bytes. So it's not that you read it as hex 4000. In that case, that will be very, very large. So that's why it's very important for you to know the endianness of the program. All right. Okay. So now let's just look back, look back to the rest of the content. At this particular position, it's always about entry point address. It tells you the offset. Sorry, it tells you the offset of, to this entire program of, the main function. So it tells you that for this particular binary, if you just read it byte by byte, just like the way that we open it, then, editor open it and then read it at this, at hex 630 byte, is the entry point, is the place that you should start to, run your program. That's the main function. Okay, and then followed by that is, the start of program headers. Again, this is the offset in this program. So this is the, offset for the start of program headers. Again, this is little endian, and that's why it has, 40 followed by a bunch of zeros. But when you interpret it, you should start with the highest one. So which is 00, and then come back like 00000, and then 40. That's why it's equal to 64. Yes.
Basically, from there, you need to right to left instead of left to right.
Exactly. All right. And then at this field, it tells the size of this program headers, which is something that we will need because when we read the headers, we need to know where to start, where to end. And it tries to save space. So it doesn't tell you where to start at, or start at offset or end offset. It only so that it can save, a lot of bytes by telling you start and the size, because usually the size is not that huge. All right. And then similarly, we're going to have section headers. We're going to have the start offset of section headers, as well as the size of section headers. Okay, so far, this is about ELF header. Any questions? Good, nice. And for you, you don't really have to read the bytes and understand it. All you need to know is that, there is a nice tool called readelf, and if you have readelf-h, it will give you those information. But I really encourage you to understand, those fields, what it means. Okay, and now let's talk about program header. I will just first talk about the content, like the format of program header, and later on, I will tell you what's the use of program header, all right? And I will talk about the use of program header later on when we, start to talk about the linker or the execution process. Okay, so program header, it tells the computer to create a process image. And when I say process image, it means that by the time that this file is executed, you need to let the operating system know that, okay, those are the chunks of the program that you need to put it into the right process places. And program headers, when we say headers, it's a table, okay? And it is a table, and each item in the table represents a segment. And those segment is a unit that the execution, during the execution process, it will move this particular segment to a particular chunk as a whole. So it's like consider this as the smallest unit that the execution process will need to like take it and move it into a process image. Oh, and yeah, let me small this again. There we go. All right, and then again, let's turn this on again. You'll remember that we said that the header, elf header occupies 64 bytes. So that means that starting from the 61st, which because we always start the offset 00. So here it's offset hex 40 is the start of program header. Okay. So this starts from this. It starts to talk about, you know, program header. Each items of this occupies, if I remember correctly, oh, yeah, it should occupy for 1, 2, so that is 16 bytes per item. So here, the order, like this is the output coming from, you know, the header abstractor, but the order is different from the way that you look at this specific byte. For your convenience, we're gonna just again use readelf, and I think it's -L. Right. So we can read this out. This is the same as this one. It should be the same. Yeah. So it tells you that for each header, what is the offset? So it tells you that, you know, this, the first line is the offset. And then the second line is the size of this particular segment. And then also the virtual address, meaning that if you're gonna copy, like when this is executed, when the program is executed, you can access this particular header at this offset. And again, this is the memory size, is alignment, and also flags means that if it's like readable, executable, or writable, so those are the permissions of this specific segment. Okay, and then interp specify the information about program interpreter. And we will talk about interpreter later. Actually, program interpreter is the tool who's going to be in charge of moving your segment around and help you to set up your processor image when you execute the program, like before you run into the main function, basically. Okay, and the rest of them are all different segments. It has different permissions. And the reason why the program is cut into different segments is because you want to have different permissions for each segment so that, you know, we don't have to have like over conservative or like over aggressive permissions for maybe your code or your executable files or your like data, right? You don't have to execute your data. So your data should always be non-executable. And actually that's part of the issues for vulnerabilities. Many vulnerabilities are because of data becoming something that is executable, which we will cover later on. We talk about like buffer overflow vulnerabilities. All right. Okay. And then comes to section header, which you can also use readelf. I think it's -S. So you will get all those sections. Again, it tells you, you know, the locations of those sections, you know, the flags, the permission of those sections. And usually those sections are putting together as a segment. And the section, the reason why there's sections here is because those sections actually use for linking when you know, convert, you know, from relocatable file to executable file. You need to put those functions or those related libraries, those information into, you know, sections. Okay, so again, this is how it looks like for ELF format binary. We have talked about headers. We talk about section, header tables. We have out headers, program header tables. And the way that it works is that the out header is the start of the program. It tells you where the program header table is, and then where the section header table is. And then starting from these two tables, you will know where are those segments. And then for section header tables, you will also know in a finer granularity, where are those sections, which is like one part of those segments. Okay, and that's about, the format. If you look at ELF statically, this is how it looks like. Then how does this works while we execute it? When we look at this, before we talk about execution, now I think it's the time for us to understand why we have two, header table. Why is there a program header table and why is there a section header table? And that's because these two tables have different use. One is for execution, and the other is for linking, like the LD, that linking process. So when we do linking, there's no program header table there. And the linker will just use section header table as an instruction to put those informations, for those data, code and data sections. And then when we talk about execution, when we execute the program, section header table will no longer be necessary. It's just like something you can consider as a dat code. You don't really need it. And for executing process, which is the interpreter, what it's going to do is to, read the program header tables and then start to operate on those segments. Okay, and then in terms of execution process, first of all, when we execute a executable file, like the .out file, we will use like exe, CVE, or similar like operating systems, kernel functions that will help you to invoke a specific executable. So what Linux kernel will do is that it will first load the executable into memory. And that's why, if you do GDB, you will find maybe heap, you will find stack, you will find those data and code into memory. And that's how CPU start to execute. It operates and read or write to the memory, right? And then how to load them into memory, that part is specified by program header table, all right? And then interpreter will read the program header table and then put them into the right place. And then how to find the interpreter, especially that different binaries will maybe have a different interpreter. It will need to find those compatible, interpreter. So to find the interpreter, it will also, come to program headers. So for program headers, there will be a specific, part that talks about interpreter. It will tell you, okay, like this is the place, this is the interpreter that you will need to use. Like here, right? So again, like the program, when it executes, it will first read the ELF header, find where the program header is. And then we'll read the program header, find where the interpreter is. And then call the interpreter will continue to read the program headers and then put those segments into the memories. All right, and then the next part is to load dynamic linkers. So dynamic linker, its job is to map the shared libraries to programs address space, for example, like libc. So it will relocate those texts and data of the dynamic linked library into the memory segment. If you use like LD, you should be able to, LDD, and then you'll be able to see, okay, what are those necessary libraries for, need to be dynamically linked to your program if you want to execute a program. All right. And then next is, again, it will continue to relocate, and it will relocate the symbol of the executable referred into a dynamically linked library. For example, if we have we use a shared library libc, and if libc is dynamically linked, means that you don't need to include like libc's printf function into your program, but instead, sorry, let me change your position. Hello? Okay. Is that, can everyone still hear me? Good. Okay, I'll continue. So in this case, suppose that we have a shared library, which is libc in this case, and then we want to use printf. Of course, that we don't implement printf, and our program doesn't contain the implementation of printf, but we want to use the printf that already installed, as part of the libc in our own operating system. So we need to tell the operating system that, hey, I want to find where printf is whenever I call it. And this is the linker's job. Linker will make sure that you can always find where your printf is. And then what if that you are running like multiple programs, where you run your program, at the same time, and then both of your programs call printf? You don't really have to, like, the operating system is not gonna map libc again in your memory, because in that case you will have many copies of libc in your memory, and that will exhaust your memory. It will eat a lot of your memory, right? So you don't really want to do that. And the nice thing for linker is that it will help you to check if the library already in memory. It's already loaded in memory. It will just like reuse that and then map the new process space. And if not, it will load and then map. Okay, so after you have resolved all those dynamically linked functions, sorry for the noise, I don't know where it comes from. And then we will be ready to start to execute the program, but we need to know where to execute. And that's the nice thing of program entry. That's why you have the elf header that tells you where the entry is, and then you can start to execute the program based on that information from the elf header. Okay. All right. So the next is x86 assembly, but we will probably start. We'll stop today for those information, given that we have talked a lot about how ELF format statically look like and dynamic how it works with operating systems, tools like linkers, interpreters, etc. All right, any questions? If not, we're gonna end our class. See you guys on Thursday.